let's go on with the properties of Z transforms. Okay, so these are all the properties that we have already seen in Laplace transform in the last semester with continuous time signals. Okay, so here we are seeing this by uh, discrete time signals. Fine, the linearity. So you need to have two weighted signals for linearity. They say that Z transform is a linear transform. Okay, why it is called as linear transform is what we're looking at. If you have x of x1 of n, the Z transform of this is given by x1 of z, and if you have x2 of n, the Z transform of x2 of n is given by x2 of z. I repeat, you have two signals. Okay, if you apply the Z transform on x1 of n and x2 of n, they're going to look like x1 of z and x2 of z as shown here. Fine. Now, since we are talking about the linearity property, okay, what we should consider is the weighted signals. Okay, a1 x1 of n is the weighted x1 of n, and this is weighted x2 of n with scalar a2 attached to this. You take the sum of these two weighted signals. So sum of the weighted signals, if you apply Z transform on that, so it is going to look like this. How? So the Z transform is linear means that the scalar can be separated and Z transforms can only be applied on the signal only. Okay, so see the scalar we have separated. We have applied Z transform on the signal, so that became x1 of z. We have separated a2 and applied Z transform only on x2 of n, and that became x2 of z. So how is this possible? Okay, we need to look at the proof of this. Every property has a proof. Okay, and we are looking at that proof now. See, if you apply if you are applying Z transform on this, okay, so what is the equation we need to obtain? So you understand this the equation, summation x of n z to the power of minus n we used to have, right? In place of x of n, in place of the input we have this input. If you remember that standard equation, okay, in that standard equation, in this place we used to have x of n because we used to see the Z transform of x of n. Now we are seeing the Z transform of this signal. So in place of x of n, we are having this particular signal. Understand that? Now bring this summation inside. On there are the two parts. Bring this summation inside along with this z to the power minus n. So when you are bringing this summation along inside along with z to the power minus n, see that this a1 a2 have got nothing to do within this summation because n is ranging from minus infinity to plus infinity, right? If you take a1 out of this, a1 and a2 out of this summation, it is not going to have any effects on that. So we can uh, take this a1 out, apply the summation here along with z to minus n. Similarly, keep a2 out, apply the summation on x2 of n along with z of minus n. Now, just observe this particular signal. Okay, just observe this particular signal. In place of x of n, we have x1 of n, except that there is no difference at all. So this is z transform of x1 of n. The z transform of x1 of n is x1 of z. So this part is x1 of z. Similarly, what is this part? This is z transform of x2 of n. So what is z transform of x2 of n? It is x2 of z. So this is how it is going to look like. Everybody's okay with this? So this is a simple proof we have for linearity property of Z transform, which says that the Z transform is linear, which means that if you have a signal along with the scalar, then scalar can be separated and transform can be applied only on the signals. Okay, that is what is the meaning of this. Fine. The next property is the time shift property. Time shift property means what? We have seen so many operations on time shift, okay, time scale, reflection in time, and all that. Okay, so here we shall see what happens if we take the Z transform of a time shifted signal. Here, if Z transform of x of n is x of z, understand this point? If Z transform of X of n looks like X of Z, then Z transform on the shifted X of n. It is shifted by n naught. Where it is shifted? Shifted to the right or shifted to the left? Can you tell me seeing this? There is a minus, it is X of n minus n naught. So this is a right shifted signal. So if you are right shifting this, okay, by what amount you are shifting? Here it says minus n naught, right? So bring Z to the power of minus n naught along with this X of Z. The same X of Z what you have for X of n needs to be associated with Z to the power of minus n naught. Why this minus n naught? Because shift here is minus n naught. If it is plus n naught, it would be Z to the power plus n naught. It is only that. Everybody understand? So if you are shifting the signal, then whatever shift you do, you give that as the power of Z along with Z transform of X of n. Everybody is okay with this? Okay. Now let's see the proof of this. See, this is the standard equation we have. In place of X of n, we have X of n minus n naught. That is what it says. If you have X of n, it is X of Z. Okay, now we're not applying Z transform on X of n, but we're applying Z transform on X of n minus n naught. So in place of X of n, you will have X of n minus n naught. Okay, this is the same equation that we had seen earlier. Now, what would happen? This, you have not seen something like X of n minus n naught Z of minus n. No, we have not seen that, right? So to bring it to a proper form, what we shall do is this. So yeah, n minus n naught is there, right? So this n minus n naught needs to be substituted as m. Why? I'm not used to see n minus n naught. I'm used to see n or m or l or k. There should be one variable here. Since there is one variable here, there should also be one variable. There are two things, n and n naught. No, I'm not comfortable with this. So to have this in the standard form of the equation, I'm substituting this n minus n naught as m. But if you do that, there is another problem that we're coming across. What is that? Okay, we can substitute this as m and we can have x of m. But here, what would this n become? If n minus n naught is m, then n is m plus n naught. So this n has to be substituted as m plus n naught. That is what we can see in the next step. See here, n minus n naught is substituted as m, and this n is substituted as m plus n naught because n is m plus n naught if this n naught is taken to the right hand side. This is how it is going to look like. Now, again, you have to think, how can we split this power of z? How can we split this power of z? This is z to the power of minus m into z to the power of minus n naught. Understand that? So we have two powers of z here, z to the power of minus m, z to the power of minus n naught. Now tell me which power of z has no job to do within this summation. This summation is running from m ranging from minus infinity to plus infinity. So m is running from minus infinity to plus infinity. So if it is z to the power of minus m into z to the power of minus n naught, z to the power of minus n naught would have nothing to do here. So that z to the power of minus n naught can be taken out of the summation. Everyone understand that point? Yeah. Here is, so if you bring that z to the power of minus n naught out, we'll be left with z to the power of minus n. Now, how does this equation looks like? Leave this x z to the power of minus n naught. Just see this. Okay. So this is a standard equation for z transform. Okay. Instead of n, we have come across m. That's it. The alphabet that we used is changed. Okay. The rest everything is same to say that this is z transform of x of m. How does it look like? It looks like capital X of z. Understand? So if you have a shift, okay, if you have x of n minus n naught, then there should be z to the power of minus n naught associated with this x of z. So that is what we have obtained here. Okay. Hope you have followed. This is the second property of z transform, that is time shift property. If you have a shifted time, okay, see the shift and bring that shift as the power of z, okay, along with x of z. So that would be the z transform of the shifted time shifted c. Everyone understand this? Okay. So let's go on with the next property, that is multiplication by an exponential. That means you have what is that? You have a signal x of n. That signal x of n is being multiplied by an exponential. How does the exponential look like in discrete time domain? It looks like a power n. Okay. So many a times we have seen. Okay, the discrete time exponential is a power n. So multiplication by an exponential means you are multiplying x of n by an exponential. See, that is what is the signal we're considering. So if you have x of n, it is x of z. What if this x of n is multiplied by an exponential a power n is the question. Then this in this x of z, z is replaced by z by. So this is how it looks like. Okay, so if it is multiplied by an exponential, okay, then this a would come with z, that is as z by a. Fine. So what is the proof for this? So you're applying z transform on a power n x of n. So in place of x of n, you substitute a power n x of n. Okay. Now after substituting a power n x of n, fine. So what we need to do, you need there are two powers of n. See here, there is one power of n here, there is another power of n here. But in the standard summation, standard equation for Z transform, minus n is what we need to have here. So is there any way in which we can convert this plus n as minus n, as power minus n, a power minus n? Can we convert this as a power minus n? Yes. It is a power n and it is as good as saying 1 by a power minus n. A power n is equal to 1 by a power minus n. So that 1 by a power minus n is combined with this z. Z to the power of minus n and 1 by a to the power of minus n. So if you combine those two, that is going to look like this. Z by a to the power minus n. This will become 1 by a to the power of minus n. So these two along with these two combined would give z by a to the power minus n. Now just observe this equation very carefully. Instead of z by a, if you had just z here, everybody listen to me carefully again. In place of z by a here, in place of z by a, if you have just z, okay, how would you write this equation? What would this equation become? This equation would become x of z. In this place, if you have z, it would become x of z. But in this place, if you have z by a, it would become x of z by a. So that is what is the proof for this multiplication by an exponential property. Everybody is able to understand that? It's a simple stuff. Okay, there's nothing difficult that one cannot understand it. You need to be able to see these equations. These equation is in standard form. Okay, if in this place we had just z, it is x of z, but in place of z we have z by a. That's why it would become x of z by a. Understand? So this is the third property we have. Fine, let's go on with the fourth property, that is differentiation in z domain. So what happens if a signal is differentiated in z domain? So that looks like this. You will have nx of n in time domain and a minus z associated with that differentiation in z domain. This is how the differentiation in z domain property looks like. Okay, so we have seen this in Laplace transform, very important property. If you multiply x of n by n, how it would change on right hand side. Okay, so you can call this as multiplying n in time domain, or you can call it as differentiation in z domain. So how this equation is obtained, okay, so needs to be understood. You should understand that we are differentiating x of z with respect to z. That means first we need to have x of z. We all understand what is x of z here in the proof. X of z is given by this. Yes or no? Now I want this differentiation in z domain. That means you need to be differentiating this equation with respect to z. Everybody is okay with that? Why we need to differentiate with respect to z? Because the differentiation is in z domain, and that too with respect to z. That's why we need to differentiate this with respect to z. So when we are doing that, you need to be doing same on the other side also. So it's differentiating the whole equation with respect to z. Let's see how it is going to get. Yeah, differentiating both sides with respect to z, we get d of x of z. But that means this we are differentiating with respect to z. Okay, and x of n, there is no z here, so this will be treated as a constant. Fine, keep that as it is. But see how to differentiate this with respect to z. So it is minus n z to the power of minus n minus 1. It is minus n z to the power of minus n minus 1. So see minus n is here, but the minus is taken out. So n is left inside the summation, and this becomes z to the power of minus n minus 1. Everybody is okay with this? Now, in this, again, there are two parts, two powers of z. Which are those? One power of z is z to the power minus n. Okay. Another power of z is z to the power minus 1. Z to the power of minus n is 1. Z to the power of minus 1 is another one. So z to the power of minus 1 can be represented as 1 by z. Okay, z to the power of minus 1 is 1 by z. Okay, and that z here along with this minus is taken on to the left hand side. So that means minus z is here. Okay, that minus z would be taken here. Yeah, minus z taken here, and on the right hand side you're left with this. Okay, or they say multiply minus z on both the sides. Okay, if you multiply minus z on both the sides, you'll have minus z here, and it will become plus z here because you are multiplying by plus z, and there is a z in the denominator. Z from minus 1 is 1 by z, so that z and this z gets cancelled, and you'll have this. Fine. Now just observe this right hand side. Just observe this right hand side. Okay, what is this? This is z transform of what? If you had just x of n in this place, it is z transform of x of n. If you have nx of n in place of x of n, it is z transform of nx of n. So this right hand side would become z transform of nx of n, that is taken onto the left hand side, and this left hand side is taken onto the right hand side. This is how the differentiation property looks like. So you need to remember all these results, because down the line we'll be asked to find out the Z transforms using the properties of the Z transform. So during that time, we need to be able to memorize these what the Z transform properties. Okay, so properties of Z transforms need to be remembered. Fine, to solve the problems. Yes, sometimes the proofs also are asked, so you need to be prepared for proofs also. Understand? So this is what is Z differentiation in Z domain property looks like. Fine. So let's go on with our next property, that is time reversal. Time reversal means it is negating the time axis. Negating the time axis means if you have x of n, give x of minus n. That means it is reflection. You can call it as reflection. You can call it as time reversal. You can call it as negating time axis. Okay, there are different ways in which the same signal can be referred to as. Fine. This is how it is going to look like now. See here, if you have x of n, z transform of that is x of z. But if you have a time reversed or a negative or a reflection of x of n, the z transform of the reflection of x of n is x of 1 by z. So in place of x of n, if you have x of n, it is x of z. If you have x of minus n, it is x of 1 by z. So negative time will inverse z is what is the meaning of this. Okay, so what is the proof of this? Proof here, x of minus n. Okay, in place of x of n, you bring x of minus n. Okay, now we are not used to see minus n here. If you want to see something positive here, what we can do, we can substitute this minus n as L or M or something else. Okay, so what we're doing here, let's see. Substituting minus n as L is being said. What we're doing, we're substituting minus n as L. Okay, so what happens if we do that? See here, there is n here, there is minus n here, there is minus n here. So minus n is being replaced by L. So this would become x of L, and this would become z to the power L. Everybody understand that? So this would become x of L, and this would become z to the power L. Fine. Now if this becomes L and L, what would happen to this? Because minus n needs to be L. Okay, you substitute n as minus L now, because minus n is L, right? So you substitute n as minus L. So what would happen? Okay, this n would look like minus L. Or if you want to see L here, you just negate this. So L equal to plus infinity to minus infinity. Yeah, that is what we've done. Okay, so substitute n as minus L means, so n is substituted as minus L. So instead of seeing minus L, if you want to see plus L, so negate this. Plus minus into plus infinity is going, right? So instead of that, it will be going from plus infinity to minus infinity, and you have x of L z bar L. But again, here this is in some standard form, but here I wanted z to the power minus L. Okay, so how to see that z prop minus L? How can we express this in terms of z prop minus L? Yeah. Z inverse to the power minus L. It's as good as saying z prop L. Okay, so it's as good as saying z power L. So z power L is substituted as this. So what is z inverse? Z inverse is 1 by z. Z inverse is 1 by z. So what is this? Now this is in this place. If you had z, it is z transform of x of L, that is x of z. This can be expressed as x of z in this place if you have z. But in this place you have 1 by z. So it is x of 1 by z. So in this place what you have, you should see. In this place you have 1 by z. So it would become x of 1 by z. Fine with that? So this is the proof for time reversal property or reflection of a signal. If you have, how what would be the z transform of that time reversed or reflected signal? Fine. Let's go on with the next property, that is convolution in time domain. Okay. Now how the convolution in time domain would look like? Okay, let's understand that. Yeah. Now again, you have not seen what convolution is as of now, because convolution chapter is module 3. Okay, convolution chapter is module 3, and we have not seen that module 3 as of now. Fine. So what we need to do is just understand the equation for this, or just try remember the equation for this convolution. Okay, so let's see the convolution, actual convolution in module 3. We didn't take that module 3 because there are a lot of sketches that needs to be done, and doing that sketches in PPT, it's troublesome. Okay, so I thought we will not take the convolution chapter. So let's take Z transforms. Okay, so we are into Z transforms. This is a small thing that is connected with the convolution chapter. Fine. Understand, what if you have a convolved signal in time domain? What would the Z transform of that would result in, is what one needs to be seeing here. Let's try and understand that. See, this star operator, what you're seeing here, is actually the convolution operator. Okay, so this can be read as x of n is being convolved with y of n. How this needs to be read? The x of n being convolved with y of n, or this is convolution of x of n and y of n. Okay, so in which domain the convolution is being obtained? In which domain is this time domain or z domain? This is time domain. So you are applying z transform on time domain signal, and when we do that, we get into z domain. The z transform is being applied on time domain signal. So when it is done, the time domain signal will get transformed into z domain signal. Understand that? Now, see here, what is that you're saying? The convolution in time domain is being transformed into multiplication in z domain. Okay, understand this point. You have convolution operator. That convolution operator would become multiplication. Convolution is a very difficult operation to perform, but you'll be performing that in your third module. Okay, but that difficult convolution operation, which involves a lot of mathematics, okay, can just be converted into a simple multiplication of two signals in z domain. So this convolution property can also be stated as convolution in time domain is multiplication in z domain. So how it becomes multiplication in z domain needs to be understood. Fine. Now, what is the proof of that? So here you have z transform of x of n and y of n. The convolution. So if you are applying this z transform on convolution of two signals in time domain, so this is the input now. So that input would come here into z prof minus n. So we have the equation for this, which you are not aware of. Okay, we have the equation for this convolution of two signals. As of now, you just see what is that equation. This is the equation for convolution. So this now needs to be replaced by this. So once you understand, once we start learning the convolution, some convolution integral, you yourself can recall this. But as of now, since this is new, you'll not be very comfortable. Just try remember this. Okay, so what we are doing in place of x of n convolution y of n, we are bringing this. That's it. How is it going to look like? Here, this is x of n convolution y. This is how it is going to look like. So that needs this particular summation needs to be brought in place of x of n. So there will be two convolutions now. One is n running from minus infinity to plus infinity, and another this k running from minus infinity to plus infinity. Understand that? Now you have got two summations. We have to rearrange this now properly. Okay. Before rearranging, see what we're doing. This n minus k is being substituted as m. How does it look like if you substitute this n minus k as m? This n minus k as m, would somebody in the chat window? Hey man, you're not supposed to chat, man. If you have any problems, you give me that. Others, please, man. Yeah. Yeah. Let's see this. So we have two summations, one running from minus infinity to plus infinity, k running from minus infinity to plus infinity, but there is an n minus k, and this n minus k is being substituted as m here. Okay, n minus k. If you substitute this n minus k as m, what would this n be? This n would be m plus k. Okay. Yes, okay. I think this got stuck. Yeah. See here, I think I should have brought another step here, which I'll be bringing maybe when I post this PPTs for your reference. I should have brought another step here by substituting n minus k as m. If this is m, this is z prof what? Minus k into z prof minus m. So z prof minus k is associated with this. Z prof minus m is associated with y of m. This is how it is going to look like. So if you observe only this, this is x of z, and if you observe only this, this is y of z. This is how the convolution operator is is converted into just a multiplication operator in z domain. That's why it very clearly says convolution in time domain is multiplication in z domain. So this can be asked for proof, like prove that convolution in time domain is multiplication in z domain. So it can be asked for proof like this. Fine. So I'll make this more clear to you, when I post this in Google Classroom. I'll have to bring in one more step which would make it clear. So if you've not understood, I'm just telling you again. This n minus k is m. If this n minus k is m, it would become y of m. What would this become? This n is m plus k. This n is m plus k. So this would become z tilde prof minus m into z tilde prof minus k. Z tilde prof minus k you associate with x of k, and z tilde prof minus m you associate with this, because n minus k substitute as m. So you have two summations here. Okay, and if you observe that carefully, so this is z transform of x of k, and this is z transform of y of m. So this is how it is going to look like. Instead of n we have k, instead of n we have m here. That's it. Okay, you can have any variable, it's not a problem. Okay, so we can understand just by seeing this that this is z transform of x of z, and this is z transform of y of m. Okay, so that is x of z and into y of z. So the convolution operator has now become just a multiplication operator in z domain. Understand that? Okay. Now let's go on with another property, that is initial value theorem. In initial value theorem, if x of n is causal, then the initial value, what is initial value of x of n? It is x of 0, because if it is a causal sequence, it starts from n equal to 0. So that's why initial value of x of n is x of 0, and that would be limit z tending to infinity of x of z. So how is that? Needs to be looked at. So this is the equation we have for x of z. Okay, so from this, suppose I want to separate 0th sample from this summation. This summation is now from minus infinity to plus infinity. X of n is causal, right? Since x of n is causal, x of n extends from 0 to infinity. That's why it becomes 0 to infinity. Now that 0 to infinity, from that 0 to infinity, I want to take the 0th sample out. So if you take 0th sample out, it is x of 0 into z prop 0. So z prop 0 become 1. So you will be left with x of 0. Then what is remaining in this summation within? So all other samples except 0. So the summation would run from 1 to infinity x of n z prop minus n. Now, what is said here? The limit is being applied. See here, limit is being applied to x of z. So you apply limit z tending to infinity on both sides. What happens if you do that? If you apply limit z tending to infinity on both sides, so this would look like limit z tending to infinity x of z. On this side, what would happen? Since in x of 0 z is not there, x of 0 would be x of 0 only. Now in this z is there, z to the power of minus n is there, so it would become 1 by z to the power of minus n. So if that z in the denominator becomes infinity, the whole term becomes 0. That's why it looks like this. So the second term would become 0 if this is z tending to infinity. So x of 0 would be remaining. So if this x of 0 is equal to limit z tending to infinity into x of z. Okay, this is called as initial value. How to obtain the initial value of x of n, that is x of 0. So that can be obtained by applying limit z tending to infinity on x of z. There is another theorem which is not very important from problem solving point of view as well as from proofs point of view. Okay, so just remember this. Here the initial value was x of n, right? X of 0. So here the initial value is x of infinity. So that x of infinity can be written as this: x of n, n tending to infinity. So this is x of infinity, the final value. How the final value can be obtained? The final value can be obtained by an equation like this. So just try remember the equation if in case the problems are asked, but most of the times it has not happened. It has not happened. Okay, they have not asked problems or the proofs of. But to be prepared for the worst, let's just remember this equation. What is this equation? This is final value. Final value of x of n is x of infinity. So n is tending to infinity. Okay. So we shall stop today's session, and I want everybody to start giving you attendance. And I've been observing till half of the class or till the end of the class, the participants are less. Suddenly, participants increase at the end, which I'm observing, and I'm taking the print screen of the attendees before and after you give your attendance. Okay, so which is not good. Those who are coming for the sake of attendance at the end of the session, okay, is not good. Maybe from next class onwards, I'll avoid people joining at the end. Okay, so that care I'll take. Fine. Maybe if you are smart, we should also become smart, and let us strive for that. Hmm? Yeah, I want everybody to start giving your attendance as soon as possible. We have less than a minute. Anytime this session will be off now. Yeah.